Hello, today we're going to look at the national grid. Now the national grid is a system that connects all the houses in this country to a power station, and the power station provides the energy for our homes, and it's connected to the power station by a whole series of cables carried sometimes by pylons but more often nowadays underground. So we're going to provide the energy here from the power station, and we've got a bulb connected to the power station to see how much energy is being given out. Then over here is our house, and our house has got a bulb as well to show how much energy the house is receiving. So you've always been told that it doesn't matter what length the leads are. When you get the leads out of the box at school, we say it doesn't matter about a short lead or a long lead. But when you multiply that up to the whole country, it does make a considerable difference. So let's have a look at what happens. I'm going to turn my power station on and look at the bulb. Then we're going to look at the house and see how much energy it's receiving. So there you go, the bulb at the power station is nice and bright. I'm giving it 10 volts here. The voltage is the energy carried by each charge. So here, each charge is getting 10 joules of energy and making that bulb light up very, very brightly. But when we look at the house, there's a problem. The bulb here isn't getting enough energy to light up. We can see that it's getting some energy. We're giving out 10 volts, but this bulb here is only getting 0.43 bulbs. Very, very little. It's lost about 9.5 joules of energy for each charge as it goes along these wires. The problem is, when a current flows in a wire, it gives off lots of heat, and these wires will be getting very, very hot. So we can't send the electricity this way. We need to put in some new things called transformers to try and help. So we need to put some transformers into the national grid. But what is a transformer? Well, it's actually quite a simple device. It's made of two coils. A primary coil, the first one in the circuit, and a secondary coil, the second one in the circuit. They're not connected together, they're completely separate coils. And when you put them next to each other and connect them with an iron core, they become our transformer. We'll learn exactly how they work next lesson. But what we're going to do is use it as a step-up transformer. So on a step-up transformer, you have more turns on the secondary coil than on the primary coil. So this is going to be our primary coil, and I'm going to use 120 turns. When we get to the secondary coil, we're going to use 2,400 turns. And what that enables us to do is to step the voltage up. When you step the voltage up, you step the current down. You can also use these as a step-down transformer at the other end of our circuit, really just by turning it round. So this time our primary coil is going to have 2,400 turns on it, and our secondary coil is going to have 120. Let's see how it works in our national grid circuit. So I've put my transformers into the circuit. On this side I have a step-up transformer. This has 120 turns on its primary coil and 2,400 turns on its secondary coil. We've multiplied up the number of coils by 20, 120 to 2,400. Into the first side of this, I'm going to put my 10 volts. And this will be connected to the bulb as well, because if I put it on the other side, I might blow my bulb. On the other side, I have a voltmeter to see how much voltage we're getting out of the transformer. Let's turn it on and have a look. So I'm putting 10 volts in, but if you look, I'm getting out nearly 200 volts. So I've put 10 volts in, 200 volts out. I've multiplied it by 20, which is the same number as the number of turns increase on our transformer. This high voltage is being sent along our cables, and when you put the voltage up, you put the current down. What's happening is that each of those electrons, as they move along the wire, is carrying more energy, so there are less electrons actually travelling down that wire. The voltage has gone up, but the current has gone down. When we have less electrons travelling, they lose less energy by resistance, and we get less heat loss along these wires. So when we get to the other end, hopefully, we're going to have enough energy to light our bulb. The trouble is we can't send our high voltage into houses, along our electricity cables is transferred at about 400,000 volts. And if we send that into houses, it's going to cause a lot of problems. First of all, it's going to destroy all their equipment, and secondly, it might cause fires and electric shocks. So back at the other end of this, we need to step the voltage down. So I've got the same transformer, but the other way around, which makes it a step down transformer. I have 2,400 turns on the first coil and only 120 on the second coil. You can see that at this end I now have a high voltage still, again nearly 200 volts. I really haven't lost much energy along my cables. And when I plug my bulb back into the other side, it lights, because there's enough energy reaching this end to light that bulb. In fact, when you look at the meter here, I have about 5.5 volts, 5.4 volts. So in the first one without the transformers, although we started with 10 volts, we only ended up with 0.5 volts, which didn't light up lamp. With this one, we start with 10 volts and still have 5.5 on the other side, enough to make our lights light in our houses. And that's the point of the National Grid, and that's the point of transformers. They convert the energy from one voltage to another voltage. So we start with a high voltage and go to a low current, send it across the National Grid, get to the other side where we step the voltage back down and the current goes back up. Because of this, we lose significantly less energy when we transfer our electricity to our houses.